You know you strip it from your pain. You know you sinner from your sin. When the heavens doors are shut, you get them open, but I know you. Give me steam, and how you feel can make it real. Real as any place you've been. Get alive with the dreamer's dream. Stay back. So stay back. Can't you see I've lost control? I'm getting to scream. You're moving in so close, still I'm picking up this heat. This heat. Give me steam. I'm how you feel can make it real. Real as anything you've seen. Get alive with the dreamer's dream. You know you're green from your red. You know the quick from the dead. So much better than the rest. You think you'd be blessed, but I know you. You know you let her from your snake. You know the struggle from the break. You know your straight line from a curve. You've got a lot of nerve, but I know you. Give me steam. I'm how you feel can make it real. Real as any place you've been. Get alive with the dreamer's dream. Everybody knows style. Hold your breath, count to 5, act slap, booby trap, cover it up in bubble wrap. Room shake, earthquake, find a way to stay away. It's gonna blow, it's gonna break. This is more than I can take. Oh yeah, I need steam. Feel the steam around me. Are you turning up the heat when I start to feel
switch off that mic and switch on that. Not working. All right, so let's just go ahead and go with my regular mic here. Sorry about that for those online. Some of the audio was missed. Hopefully it's back. Yep. There we go. All right. So anyway, sorry. So we're going to go in, we're going to come into A, and we're going to process it immediately. We're going to process it the very first time that we see it, because we want to make sure that it gets done. Right? Now I have two choices here. I can either go left or right. So let's just go ahead and say that I go left here. Now, at this point, I'm on. Think of this as a person just walking, right? They walked from A and then they walked down to B, and what they're going to do is they're going to process A, or process B now, right? And again, what do I mean by process? Well, there's data stored in that node. You would compare it to whatever key value you're looking for. You would print it out, whatever you're going to do with it, right? We went left. Go left. Okay. Let's do that again. We'll go left again, go left. And then at that point, we're at C, so let's go ahead and process C, right? Or sorry, D, right? Now we're here. There is no left child, there is no right child, so we've hit a dead end. And if you're traversing a maze, what happens if you hit a dead end? You back up. So we'll come back up here, we will return to parent, and then note here that we've already gone to the left child, so we don't want to do that again. We don't want to look at the same thing twice because we're considering simple graphs, simple cycles and simple lists, or simple paths. We don't want to traverse the same edge more than we have to because that would be wasting time. So now we're back up here at B. We have already gone left, so now let's go right. So we go right. Go right. At that point, we're at E, so let's go ahead and process E, right? And then we're done because there's no left child, there's no right child, so we go back to the parent. We've already processed the parent, we did it right here. We've processed its left child, we've processed its right child, so the only thing to do now is to go back up to A, right? Which we've already processed, so we go back twice here, right? We're going to go back, and now we're at A. And now we go to the right child here. C, and so we process C. All right, and then we go to the left child, but there is no left child. So we end up not doing that. So we end up going to the right child, and we end up processing F. Right? And this is what's known as a pre-order traversal. Let's think of this more generally. What if I just had a parent, and then a child, U here, or let's go with L and R. L and R. There we go. So the order that we're going to process this in is going to be P, L, R. Or generally, we're going to process the parent, then the left, and then the right. That's the order that we're going to go in. And you can kind of see that this is going to be a recursive process, or at least it looks recursive. I'm not going to show you the recursive process until the end. I'm going to show you the proper stack-based process to do this instead. But this is a pre-order traversal. Let's do it on the same example here, but let's do it a little bit more systematically and see if we can develop an algorithm for it. Okay? All right. So what I'm going to do is I'm going to establish a stack. Come on, get rid of all that. What I'm going to do is I'm going to establish a stack over here. Now, why did I immediately go to a stack? Well, think about what you're doing. You're going down deeper and deeper and deeper into this tree. You need to keep track of breadcrumbs. You came from A, you went to B, you went to D. How do you know how to get back up once you're done, right? You're going to come back up by popping it off. You're going to go A to B to D. If I pop off D from the top, then that takes me back to B up here. So I'm going to use a stack to keep track of where I've been, all right? All right, so we need to get things started first of all. So to start, initialize. Well, first of all, we need an empty stack. Empty stack. And then to get this entire process started, what I'm going to do is I'm going to push the root. S.push the root. Oops. Root. And now it looks like this. A is at the bottom. Okay? I'm also going to repeat this. Right? I'm going to repeat going left or going right or going left and then going right. And I'm going to repeat it until I'm done. I've explored A and I've explored the entire left subtree. I've explored the entire right subtree. And when I return back from it, that's it. There's nothing left to explore. The condition for doing that will be while my stack is not empty. While S is not empty. Right? Dot, dot, dot. Right? I need to go to the stack and say, all right, let's pop off whatever's in the stack. S.pop. And so what I'll do here is I'll keep track of U here. And A has now been popped off. What should be my next operation? I compare or process or whatever that means for you. Print, whatever. So let's go ahead and process U. Okay? That means I print it out, whatever. I compare it, and it's done. Okay? Now I need to set myself up for the next loop. What do I need to do now? I need to push B and then push C. What if I did it that way? Right? When I come back in at the top of the while loop, what's the first thing that comes out? It's going to be C. Is that the next thing that I need to process? I said that I was going to go left first, right? So I need to go in the opposite order that I'm expecting them to be processed in. So in this case, I would push what? C and then B, right? So let's do it in that way. S.push, use right child, and then S.push, use left child. Now do be careful here. What if it doesn't have a left child? What if it doesn't have a right child? Implicitly in my pseudocode here, I'm saying if it exists. So it's like a null pointer check. If the left child exists, then I'll go ahead and push it. If the right child exists, then I'll go ahead and push it, or the opposite order, but whatever. There. There's my while loop, right? So let's continue this, okay? The next iteration, I come back up to the while loop and I pop what's on the top, okay? What's on the top now is B. There we go. Actually, I should just carry it over, right? Pop off the top, and B comes over here. I process B. So let me write up here the order in which I do these things. A and then B. And that's been processed. Okay? Then I push the right child, then I push the left child. The right child is E, the left child is D. So E and then D. Okay? Next iteration, what happens? The thing on the top is popped off. Now I'm looking at D. Right? I process D. In other words, I'll print it up here. And then I will push its right child and its left child. But is there a right child? Nope. Is there a left child? Nope. So I come back up to my while loop at the top here. And what now gets popped out? E. Right? And I'm back, oops. Oh, okay. I lost it. E comes over here. There we go. All right. I process it. In other words, I print it up here. Now that's done. And then I push the right child and then the left child, but guess what? They don't exist, so I leave it as is. The next iteration now, I basically returned all the way back up to A, and now I'm looking at C, which gets popped out. So C is processed, right? I pop C, I process C, now I push the right and I push the left. There is a right child, F, but is there a left child? Nope. So that's all that ends up getting pushed onto the stack, right? All right, next iteration, F comes up over here. We print it, and at that point, there's nothing left to push. There's nothing left to pop, and so the stack is now empty, and we break out of this while loop here. Right? Let's do it on a slightly larger example, just so that we get the hang of it before we actually implement it. Right? So let's bring in a larger tree, that same tree that we were working with before. Right? There we go. I won't draw the entire stack in this. If you want to, you can see my video animations on the pre-prepared videos. But instead, let's just go ahead and speed run it. We'll go ahead and go start at A here. All right. What's the next thing that gets processed? Well, here's a hint. You're always going left, and you're always processing as you go. So it's going to be A, B, D, G, L. And remember that it's root, left, right. Okay? Once we're done with L, there's no left child, there's no right child. So we come back up to G, but G has already been processed. So we go down to the right child here. M, and then we traverse left, so R. At this point, this entire subtree right here has been processed and we're done. Okay? I come back up and I go right. I process H. I would have processed its left child first, but it has no left child, so I don't end up doing that, and I just go to N next. Right? At this point, all of this has been processed. Right? So I go to E next, and again, E doesn't have a left child, so I don't process it, but I do process it before I do that. And then I and O. All right, you guys help me out with the rest of them. What's the next one? C, F, J, yeah, it's a J, all right, P, Q, and then K at the end, all right? All right, hopefully that's a good understanding right there. There's my test case. We're gonna come back to that and see if we can program this correctly, all right? So let's come back over to our Java demo that we were working with last time. And I've got a binary tree here, but it's not complete. Right? We need to add some stuff here. Well, the first thing I want to do is I want to fully flesh out this binary tree node here. Right? And that means that I want a constructor. So let's go ahead and generate a constructor using fields. And the only field I want in this case, let's go ahead and deselect all of these. The only one that I want is the actual element. Right? And we'll go ahead and generate that. Okay. There. All right. And then we'll want a bunch of getters and setters for everything else. We do want setters here just like we wanted setters in our linked list because we might want to change things. We might want to change the shape or the topology of our graph. So let's go ahead and generate getters and setters and do them all. All right. Select all. Right. There. Okay. Before we continue, is there any other things that we might want? So we're just thinking about a binary tree node here, right? In isolation. Right? Think about B here. Is there any question that you would want to ask B? One question I would have is, are you the root? Right? So what is the answer to that? I'm a root if and only if what? If the first node, how do I know that I'm the, how does A know that it's the first node though? It has no parent, right? So public Boolean is root. Return this dot parent is equal to null. Right? If it's equal to null, then it has no parent and therefore it is the root. Right? What else would you want? I can get the left child or I can get the right child. What else might be convenient? A Boolean. Yeah, do you have a left child? Has left child? Right. Has right child? How do I know if I have a left, left, right, whatever. Left, I meant to do this one. Left first. Left to right. Right. How do I know that I have a left child? If it's not null. Right? Is that the correct logic? Nope. What's the correct logic? If it's not null, then I have a left child. And if it's not null, then I have a right child. Is there anything else that might be useful? The number of children, right? We could say, how many children do you have? Do you have 0 children? Do you have 1 child? Do you have 2 children? That might be useful later on. We'll come back to it. What other types of nodes are there? If you're not a root, you're a what? There are 2 other types of nodes. Do you remember? Yeah, what's R, for example? It has no children, so it's a leaf, right? So let's ask you, are you a leaf? public Boolean is leaf. How do I determine if I'm a leaf? Or if I do not have a left child, do not has this dot has left child, and, or translated, and this dot has right child. If I don't have a left child and I don't have a right child, then I am a leaf. Right? I'm a leaf on the wind. Right. Is there a way to simplify that? 235. If you have not and not, you can factor out, right, a not, and then it becomes what happens to the, yeah, what happens to the and becomes an or. What is that called in logic, at least? Yeah, it's De Morgan's law, right? And just remember the pirate. I guess he's not De Morgan. What is he? Yeah, Captain Morgan, right? Captain Morgan's a pirate. Right? So there you go. That's how I always remembered it anyway. Right? All right, so that looks a little bit fleshed out. What else do we need? Let's see. Yep. What I'm going to do is I'm also going to give myself a constructor over here in the binary tree. Let's go ahead and make a default constructor. Right. By default, what should happen to the root? Have you put anything into this tree yet? Nope. So I'm going to make it null. And just because I've got a demonstration here that's going to have to, it has to work if with this constructor here, root, and I'll do it like this, right? Because what I've done over here in tree utils, I've created that same small graph with A through F. And what I've done is I've manually set who the left child is and who the right child is, right? And I've also done it for this large graph over here, right? I've done A through R, and then, for example, A, I set its left child to B, I set its right child to C, right? In other words, this graph right here, because this is going to be my test case. And so I manually built this graph right here, right? And what problem are you? Are we in a binary tree? Well, A is what? A is a binary tree node. Why are you, string, okay. And why are you binary tree? Node. Oh, sorry, there we go, node, there we go. There, I just misspelled it, okay. Now over here in the demo, that means that I can actually create this binary tree of strings, right? A, B, C, D, E, F, G, etc. And I'll go a large tree, right, is equal to tree utils dot the large tree, right? Now what I want to do is I want to perform a in order traversal on this thing. So to do perform on in order traversal. Well, where should that belong? Should I go ahead and write a public static void pre-order traversal, and I'll take in that binary tree with a bunch of strings? Does that belong here in the demo class? No. That sounds like a tree thing to me. Where does it belong? In the tree class, right? So let's go ahead and public. I don't know what the return type on this will be just yet, but I'm going to call it pre-order traversal. Right? I don't need to give you a tree because I am the tree, right? This is the tree, okay? So what is it going to be our return type here? Let's just make it void for now. Okay, I don't want to have to think about that. We'll come back and maybe redesign that here in a little bit. All right, but I'm going to need to translate this pseudocode over here where I initialize an empty stack, I push the root, and then I go into a while loop while the stack is not empty. Right? So help me out here. How do I create a stack in Java? I could do a stack. What's even better? It was the double-ended queue or the deck, right? Of elements of type T. I'll call it stack because I want to treat it as a stack. As a new, I don't know, let's go with linked list. That was one of the implementations. There we go, bring that in, import that. and my deck, my double-ended queue, import that. Remember, that's just an interface anyway. A linked list is an actual implementation of it. So I initialized an empty stack. The next thing I need to translate is I need to push the root onto that stack. Right? So stack dot, guess what? Push, right? And I need to push this dot root. It's not going to like that though, right? Because I said, well, you know, if I've got a tree of strings, then I would end up pushing a string. But does a string give me its parent, its left child, or its right child? No. So what am I actually pushing onto the stack? A tree node of elements of type T, a binary tree node. Right? Okay. When I pop it out, that will allow me to go to the left child or the right child, get its element, the actual string that's stored in there, or I could go back up to the parent if you want. Right? Now I need a while loop. Right? While the stack is not empty, let me just go ahead and translate everything over here. U will be equal to stack.pop. Okay. And then I process U, and then I will say s.push use right child if it exists, and then s.push use left child. All right, all of that is just pseudocode there. Help me out here. How do I tell if the stack is empty? Oh, I could do the size, but remember that it has this nice interface where it says, it tells me if it's empty or not. While it's not empty. Right? Well, this is almost a one-to-one translation here. I just need to know what type of variable this is. Right? And let me show you a trick here. That's actually a trick that you probably shouldn't use, that I would advise against using. Right? Oh, that worked. What is var? Variable, right? It's not a parameterization, right? This is something that was adopted from C#, where, man, I am so lazy, I don't even want to type out the type, right? I will let the compiler determine, oh, well, it pops out a binary tree node, so I will replace var with a binary tree node here. I won't have to worry about that. That's the stupidest shortcut I've ever seen, right? It just saved you typing on one line and one line only, and it made it more confusing, right? What's its type? Well, I have to look up here to see what types I actually put in my deck, right? Versus just type it out. You just type it out once and you're done, right? But that is something that was added in Java several versions ago that I've never used and I never cover because it is such a stupid feature. Right? All right, what does process U mean? Let's translate that now. That means comparing it. It means printing it out. Let's just go ahead and print it out. System.out.println U. Okay? We'll figure out, we'll come up with a better solution later on. Right? Now, how do I push something? Well, I need to push use right child. U.push, or sorry, dot get right child, and then get left child. But this ain't pseudocode. You have to consider, what if they don't have a left child? What if they don't have a right child? Should you be pushing them? Nope. Stack and stack. Right. So let's surround this with an if condition. If U.has right child, I'm glad that we invested some time in there to think about what we might want in the future. If U.has left child, because it becomes so much more convenient now that we have those things, otherwise we would have gone back and added them anyway, right? All right, there we go. Let's come over here to my demo and see if this works now. Let's get rid of this because that was bad design. Large tree dot pre-order traversal. Right? Now if I run this, it should come up with this ordering because that is in fact the tree, right? A, B, D, G, L. Let's print it out. Go over here to console. Ah, darn. What else do I need in my node? A toString method would be nice, right? Public string toString. And you know what? I'm just going to print out return, or I'll return this dot element dot toString. Okay, there we go. Actually, I don't want to go toString there. If the element is null, then it'll end up printing out null. I guess I have to. Dot toString, fine. I'll do it that way. There is a better way of doing it. There's the okay way of doing it. Here's the better way of doing it. String dot value of this dot element. There we go. Return that. What that's going to do is, if that element ends up being null, it will return null, right? And it won't end up being a null pointer exception. This would end up being a null pointer exception if this are null, right? But generally, we're not going to allow null values. All right, so let's see if this worked. ABDGLMR, ABDGLMR, HNEI, HNEI, blah, 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 blah. I think it's right. I can put them side by side. There we go. QK, J, P, right? Looks like it's right to me. Right. All right, so we were and by the way, it executes and it terminates, right? So that's nice. Is there a better way that we could design this? Right? Well, sometimes you don't want to just print it out. Sometimes you want to make a comparison. Sometimes you want to do something else. Right? What if we returned something instead? A list of elements of type T. List, and it doesn't matter what kind of list here. Result is equal to new array list. Let's just go with the new array list here. And now what it means to process, it means to add it to that list. Dot add u dot get element. Right? And let's go ahead and import that. There we go. And I need to return the result. Now in my demo class over here, I can go ahead and run it, but it won't print anything anymore. But what I could do is I could capture that value. Pre-order is equal to that. And then we can sit, now I'm interested in printing it out. Println pre-order. There we go. And there. Same as before. Right? Let's make sure. A, B, D, G, L, M, R, H, N, E, I, O, C, F, J, P, Q, K. Looks correct to me. Well, that still doesn't seem all that satisfying, because why would you put stuff into a tree just to dump it to a list, right? If you're going to do that, there's no purpose of a tree, right? That's just a list with extra steps. So is there a better way that we could do this? What I would like to do is something like this. For each element string S in the collection large tree that performs a pre-order traversal, then system.out.println S. That's what I'd like to do, because it's a collection, right? And in Java, how do we iterate over collections? We do it through enhanced for loops like this. Unfortunately, it's not going to work because this is not iterable. All right? Let's make it iterable. This is going to be required for you to do on your last assignment that's due Friday of Dead Week. So implements iterable P. Okay? Now, what implements iterable means is that you can now use it in an enhanced for loop like this over here. Did we do this with linked lists? I forget. Nope. Okay, we're going to do it with binary trees. And that means that it has a method that returns an iterator. All right, there we go. By default, it's not going to generate code for you. It's just going to return null right now. But this should work. Why are you still complaining about this? Only iterate over array or instances of iterable. You are iterable. Let's go ahead and get rid of that. Get rid of that. Oh, I put it on the wrong one. What the hell am I doing? I put it on the node. A node can't iterate over itself. It's just one thing, right? But a binary tree can iterate over itself because it's multiple things. So now we'll add unimplemented methods. There we go. And now that'll compile. And let's go ahead and get rid of this now. Where is it? Yeah, let's get rid of this iterator. Okay. All right. See, the demo class now works. Obviously, it's going to crash because it's going to end up returning null, right? So null pointer exception. We actually have to write that code. Okay. All right. Hopefully, I can remember how to do this off the top of my head. Return new iterator of elements of type T. There we go. That will create a brand new iterator. Do we remember what this is called, by the way? This is an anonymous inline declaration. Right? I could have a class called my awesome pre-ordered traversal iterator. Right? In fact, we could do that. And I would have to put that in a class. That would be a named class. This is an anonymous class. It has no name. Right? It just implements this iterator interface. And it requires these three methods. 3 methods or 2 methods? Yep, just 2 methods. Right? That's because one of them is now default, and I forget what the default is. I think it just throws an exception for the third one. But these are the 2 we need to focus on here. Right? What I need to do is I need to take this algorithm right here, and I need to translate it into these 2 methods right here. All right. To do that, what are the 2 methods? One method says, do you have another thing that you need to continue going and exploring? Do you have another one to explore? Well, what would be the equivalent up here? The stack, is it empty or not? Right? So that means I need a stack, first of all. Right? And I will put that into the iterator right here. Right? I now have my stack. I now have, do you have another one? Well, is the stack empty or not? If this dot stack is empty, then if it's not empty, then yes, I do have another one. Right? All I'm doing is directly translating this thing right here. Right? Now get next, right, or just next here. That is all of the other functionality. What you have to do is you have to pop it off. You have to make sure that you are eventually going to return it. Right? So I will pop it off. Right? Oops, I meant to copy. Right? There's the thing that I want to return. Oh, not. I wanted to copy that one right there. That right there. Right? I pop it off and I ultimately return you. Right? But be careful. You also have to set yourself up for the next iteration of this loop. And there is a loop here. It's an iterator loop that's being performed in the main right here over this enhanced for loop. Right? So to prepare myself for the next iteration, I take the rest of this stuff. I don't do this because ultimately I'm returning it, and now it's on you to process. So I set myself up for the next iteration here. If you have a right child, I push it onto the iterator stack. If you have a left child, I push it onto the iterator stack, and then I return u dot get element because I'm not interested in the tree node. In fact, that would be a leaky abstraction. Right? There we go. Does it work? Well, remember what it was before. Let's go ahead and show this down here. There's my expected output. Oh, come on. Oh, what else did I forget? I created my stack, but what else did I forget? I need to push the root. This is going to be a good question. What is this referring to at this point? Yeah, the iterator. So this dot stack is pushing that dot root or this dot root? That's a good question. Are you able to do this? Oh, come on. Darn it, I forget how to do this now. Because it's an anonymous class, we can't have a constructor. So I can't do this. I'm not going to remember how to do this off the top of my head. Can I push the root? So this was working before. I can't put it into a static block, darn it. But I can... What I could do is list.of root. That's a quick and dirty way of doing it. What did I just do there? I created a linked list that has what in it? One thing, the root. Right? All right, that's it. I'm cheating. This will work though. All right. There we go. A, B, D, G, L, M, R, H, N, blah, 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 blah. There we go. All right. So I forget, I think I can bring this up. How do we do this without, where's my iterator? Do I have an iterator? Nope, I don't have one in this example here, but darn it. How do you can't do that. All right, so maybe, I mean, we've got plenty of time here. Let's go ahead and say, all right, fine. This might be a use case where we cannot use a pure anonymous inline class like this. So let's go ahead and create another class here called new pre-order iterator. There we go, and there we go. And it implements iterator of elements of type T. There we go. And we don't return. Instead, we've got a stack. And I'm not going to cheat anymore. In fact, I'm not going to cheat at all. I'm going to have an actual public pre-order iterator. And what do implements? Spell it right. Right. And it's going to be an iterator of elements of type T. And this is going to be an element, okay, T, so we need to, parameterize that as well. And now my, what do I want to call it? The constructor here will say this dot stack is equal to new, did I copy paste it? Yeah, new linked list. And I won't cheat, instead this dot stack dot push, and then this is going to take on a binary tree node T root, right? And we'll push the root in the constructor. There we go. And why aren't you format? Okay, because it's not compiling because we've got that. Now you can format. There we go. There we go. All right. So that's how I'm not cheating, that I have to actually give it a constructor. Anonymous inline classes cannot have constructors. Right? And I needed to do some operation. I needed to do this operation to get everything started. Right? So I'll leave this because if it's eventually in the notes, you'll want to see it. But let me go ahead and just comment it out. And now what does it look like now that I put it in its own class? Return new pre-order iterator with this root as your starting point. And I didn't break anything, did I? Nope. Let's not print those. Let's print spaces instead so we can see it nice and pretty all in one line. ABD, GL, MR, blah, 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 PQ. Okay. There's my pre-order traversal. All right. So I did it there is a way to do it. I forget how to do it though. It's going to really bother me. But anyway, there's two ways of doing it. Let's go ahead and get rid of that list. And by the way, that's probably the most versatile way to design this, right? Because now none of the actual logic to processing is inside of the collection itself. In this case, the binary tree. You want to process strings. That sounds like, you know, a string, not a string thing, but that sounds like that's your responsibility. If you want to compare it to find a particular element, then that should be done outside of the class here, right? Instead of printing it out, I would see, is that the thing I'm looking for? If s dot equals, I don't know, what? I'll look for my first initial here. Then I'll say print system.out.println found you, right? This processing here, whatever you're ending up doing, that's not a tree thing. It doesn't belong in the tree class. Instead, what belongs in the tree class is the ability to iterate over the things and find what you're looking for, right? All right, so found you. What other tests could I do here really quick? Is Z in that tree? No, so I should expect it not to print out anything, right? There we go. All right, before we adjourn, tell me about the complexity of this algorithm. 1, what is the input? A tree. 2, what is the input size? Well, you could tell me the number of nodes, n, or you could tell me the number of edges, m. But guess what? What was that observation that we made about trees? M is equal to n minus 1, which is order n. So does it matter which one you choose? Nope. We'll go ahead and go with n. Right. 3, what is the elementary operation here? There are a couple of options. A node processing process. Right? B, an edge traversal. Right? Because what are you doing? You're traversing a node and then you're going over to the next node. That's one thing. That's kind of like linked lists next. Right? That was the most expensive thing with a linked list. Going next, 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 next. Right? Node processing or edge traversal. What if we went with A here? How many times do we process each node? Once. Hopefully you're not processing a node more than once. And so we have order n. Right? What if we went with edge traversals? Think about this a little bit more though. When we go from A to B, right, we do eventually come back. Right? We're actually coming back up here to A because we've traversed this entire left subtree and then we come back up. So 2n, which is every node, every edge gets processed or traversed twice, which is going to end up being order n. So does it matter? Nope, it's still going to be linear. All right, so did we achieve our goal, by the way? Let's not lose the forest for the trees here. Right. What was our ultimate goal? We want efficient general operations for our data structure here. If you have to perform what is essentially a linear search to find what you're looking for, we have not achieved our goal. Ultimately, what you have to do is you have to search everything to find that needle in the haystack. We're back to linear search for this. But we did achieve one goal. We proved that this is a viable data structure because we can get to every single piece of data if we have to. Right? When we come back on Wednesday, we'll look at 2 different traversal strategies. The pre-order traversal strategy was the root, then the left, then the right. We're also going to look at an in-order traversal, which is going to go left, root, right, and a post-order traversal. Post-order traversal, which is following that pattern. What do you think? Left, right, root. So what's the difference between all those 3 things? Just simply when you process the root. Do you process it the first time you see it? Do you process it the second time do you see it? Or do you process it the 3rd time you see it on your way back up? Right? Each one of those has different applications, by the way. And each one of those 3 things is used in practice on all trees. Right? And then there's finally the 4th one that we'll look at is a BFS, which is a breadth first search traversal. And we'll look at all 4 of these. We've already looked at the first one. They get increasingly more difficult to implement, but then it gets really, really simple with BFS. So we'll save the best one for last. All right, we'll see you on Wednesday.